Welcome to this video on the definition of limit. So here we are gonna calculate the limit that you see in the screen by using the very basic definition of limit without using the calculus, the rules of limits. So in order to do this, we first need to have a guess on what the value of the limit is. And so to achieve this, to have this guess, we are gonna simplify this function first. Since 1, the value here, the x0 value here, is a value for which the denominator of this function becomes 0. So it's not part of the domain of f, so we cannot calculate f of 1. So let's do this. So let's write our function f here. So we decompose these two polynomials. So the numerator becomes x plus 2 times x minus 1, and the denominator is simply x plus 1 times x minus 1. So this is done. And then the 2x minus 1 can be simplified, and so we obtain x plus 2 over x plus 1. And so now a limit here can be guessed. So this converges as x goes to 1. And let me say that so far, this is only a guess because we pretend not to know the rules of limits. And so we just guess it, and we'll verify it in a rigorous way just below. So as x goes to 1, the numerator goes to 3, the denominator goes to 2. And so we guess that the value of the limit is 3 over 2. Right. Okay, let's verify this. So first thing to do is to write down the definition of limit. So this is quite technical. Let's do it. For all epsilon positive, possibly very small, there exists delta positive, so that for all x, here I have to write the domain of f excluded 1. Now the domain of f is r excluded minus 1. 1, so the point 1 is already excluded. We have the following. So if x is close to 1, so if the absolute value of x minus 1 is smaller than delta, then what we need to have is that the absolute value of f of x, namely x squared plus x minus 2 over x squared minus 1 minus 3 over 2 is less than epsilon. Perfect. So just very briefly, let's recall what this definition means. So we've got the real line, the point 1 just here. So let's draw a very a simple function here. Suppose this is f of x. In 1, the function may not be defined as in this case here, or it may be defined somewhere else, like here, for example. So what does it mean that the limit is a value L here on the y-axis? So suppose this is L. So this means that we can, for any possibly very small region around L, so this is, let me write, this is L minus epsilon, this is L plus epsilon. So let's draw this yellow band here so that this is clear. So this condition here means that the function f has to be close to 3 over 2. In this case, 3 over 2 is our value L, and so we have to be in the yellow region. So when is the function f in the yellow region? Well, here in this area, in this part here. So we ask ourselves, can we find an interval around 1 here so that all values of f around 1 end up in the yellow region? And the answer is yes. It's enough to select, for example, this region here. We just do this, and you see, so this is now gonna be 1 plus delta, this is gonna be 1 minus delta. And so you see that this is, in this case here, in this example here, the definition is satisfied if the distance from x to 1 is smaller than delta. So if we are here, then the distance, then we are in the yellow region. So we are here, this part here. So this is just the meaning of the delta epsilon definition of limit. So now we've got to verify this. So it is usual to start from the end because we need to understand how to choose an epsilon. So what we do is we take epsilon positive, we don't know what it is, it's arbitrary, so possibly very small, and x in R, but not different from -1 and 1. And so we try to simplify this expression here. In other words, we try to understand what does it mean for f to be in the yellow region here. So let's do the calculation. So I'm just asking x squared plus x minus 2 over x squared minus 1 minus 3 over 2 less than epsilon. So how can we simplify this? Well, we go up and we remember that we already did this calculation, and actually my function f of x can be simplified in this simple fraction. So let's write this. Absolute value x plus 2 over x plus 1 minus 3 over 2 in absolute value. This has to be less than epsilon. Good. So next step is to do this difference of these two fractions. So let's do it. So what we obtain is 2x plus 1, 2x plus 4 minus 3x minus 3. And this in absolute value has to be smaller than epsilon. So note that these are all if and only if, so I'm just writing equivalent formulations of the same statement. So let's keep going. So here in the numerator now we have, so what do we have? We have minus x plus 1 over, let me write x plus 1 in absolute value, and the 2, I'll put it on the other side. Right, so now observe that this is nothing else than this. X minus 1 absolute value over absolute value x plus 1 smaller than 2 epsilon. So now we have to find here, look for a condition on the absolute value of x minus 1. Like here, we have to find the delta here. So if you look at this expression that we have here, x minus 1 is already there, so half of the job is done. However, unfortunately, we have this x plus 1 in the denominator. But now, it's enough to observe the following. So suppose that actually we take x in 0 plus infinity minus 1. So we suppose, in other words, we suppose that x is non-negative. And we can do this because actually the game here is to do the limit in 1. So if we do the limit in 1, certainly we can suppose that x, if here we have 0, that x is in this region here. So if we do this, what we have? Well, this implies that the absolute value of x plus 1, which is this factor here in the denominator, which we didn't like, is in fact equal to x plus 1 is certainly non-negative because x is non-negative, so its absolute value vanishes, and x plus 1 itself, since x is non-negative, is certainly larger than 1. So in particular, this gives a very simple bound, which is absolute value of x minus 1 over absolute value of x plus 1. This is less than or equal to absolute value of x minus 1. And what I want this to be smaller than 2 epsilon. Right? This is what I need. And so, in conclusion, what we found? We found that if x is non-negative, x is different from 1, and the absolute value of x minus 1 is smaller than 2 epsilon. So this is satisfied. So in particular, this is satisfied. And so we go up these arrows here. So this is satisfied. You go up and we ended up in here. So we find that this is satisfied too. So this guy here, these conditions here, they imply this, which is what we wanted. Good. So it's enough to choose. It's written here. The delta we need is written here. You see, x minus 1 absolute value smaller than delta. It's enough to choose delta equal to 2 epsilon. And that's it. Right. Is this fully correct? Well, almost correct. Why? Well, the thing is that this argument is correct as long as x is non-negative. And so here, in principle, for this definition, in order to have automatically x non-negative, we have to put delta smaller than 1. Otherwise, this argument doesn't work. And in principle, it's possible if epsilon is large. So how to solve this issue? Well, you just need to do the following. You put delta, the minimum, between 2 epsilon and 1. Good. This concludes this exercise, in which we have shown how to use the definition of limit, namely this one, to show, so this is the definition, this was the definition of limit, to show in a rigorous way, to calculate in a rigorous way the limit of a function in a point. Thank you for listening.